This week we're going into air pressure. I don't think maybe a lot of you think about air pressure as being an atmospheric variable. Uh, we all talk about temperature, we talk about moisture, we talk about precipitation, but we don't talk about air pressure. You started off this semester talking about highs and lows, and that is air pressure related. So we're going to deal a little bit about how the atmospheric pressure changes with time. So, and what is the significance of that? So, first you got to understand what it is. A little bit about that. Force. What is a force? Well, force is a mass, and we're going to take a mass as being molecules. So, if you were to gather all the molecules in a certain area, be it like in a wall or in a gaseous state like the atmosphere is, that's a mass. Then you multiply that by the acceleration of these molecules. Well, molecules move in all different directions, and by doing that, they provide a force all around them. And that force, that acceleration, times the mass of the number of molecules you have, gives you a force. So, a force is what really makes atmospheric pressure. The total air pressure is basically the force of all these collisions on an object. So if your body is getting bombarded by air molecules, which it is every minute, that force on you is the weight of the air on you. And Dalton law says that, we have carbon dioxide, we have oxygen, nitrogen, water vapor, all of these vapors in the atmosphere. Well, each one has a force, a pressure. When you add them all up, that's going to equal the total pressure that we're going to see at the surface. So there's two parts to this. One is you have the number of molecules and the weight of those molecules. In other words, molecules aren't weighted equally. Nitrogen molecule, carbon dioxide molecule, a water molecule, each one of them has a different weight. So the more of one you have versus another, you're going to have a different mass. Now, the weight is the force of gravity exerted on that mass. Basically, the atmosphere is always having gravity pulling all those molecules down. Yes, they're moving around, but we also have the pull of gravity accelerating them towards the ground. So with that, the number of molecules we have, the more of those molecules times the acceleration of gravity is going to give you the mass, the weight of the atmosphere's pressure. Normal pressure is basically 14.7 pounds per square inch. So that's not a lot, but if you think about how many square inches are in your body, that's a lot of weight. How do we measure this? Well, we learned first to measure it by an instrument called a mercury barometer. What a person did was he took out all the air in the tube and then put that tube into the pool of mercury and discovered that the mercury went up the tube quite a ways. That's when we discovered that, hey, this air that's all around us weighs something. So we learned that with the mercury barometer, but there are a lot better ways of measuring this than just using a mercury barometer, especially since mercury is kind of poisonous. So now we use things like aneroid barometers, which have chambers that do the measuring, and barographs, which measure and keep a track of how the pressure changes. All of these are other means. If you were at home and have a home barometer, I will bet you that it measures everything in inches of mercury or inches. And if you look at a weather map, which you've been doing a lot of now, you're going to discover everything is in millibars. The difference is significant. And the reason we use millibars to measure things is because then you can correct that to something called a Pascal. There's a 1-to-1 equivalent, literally. And Pascals are metric units, and they're much easier to work with in equations than measuring in inches of mercury. So that's the only significance here of why we use millibars, is you want to make the equations simpler. Here are some of the lowest pressures and highest pressures you can see. Highest pressure ever recorded in Siberia, 1083.8 millibars. Lowest pressure, 870 millibars. So about 200 millibar difference between the highest and lowest pressures ever recorded. All right. The atmosphere has a whole bunch of molecules going up. The air goes up a ways in the atmosphere. And since it does, the number of molecules down by the Earth is more than the number of molecules that are higher up. If you are breathing the air as you go up a mountain, you'll notice that, at the bottom of the mountain, you breathe pretty normally. Well, if you go up the mountain, say 10,000 feet up, you don't breathe so well. I went to the Rockies couple times now, and when you're out there, down in the valleys or whatever, down before you start up the Rockies, you can breathe pretty well, even at 5,000-6,000 feet. And then where I started out in Boulder was right around a mile up, about 6,000 feet up. I never noticed the altitude, just a little bit there only. However, as I went up on the mountaintops, around Estes Park or up even higher into the Rocky Mountains, and got up around 13,000 feet, I could tell the difference. It made everything a whole lot harder to breathe. That's because the number of molecules are much less. So the density is going to be significantly less. Density is less, air pressure is less. So why all these molecules down by the ground? The reason is because of gravity. Gravity is pulling all this air down towards the ground, and the air in the atmosphere is compressible. So it literally compresses the bottom layers of the atmosphere so that more molecules are in them and less molecules are up higher up. So that's why when we do the standard atmosphere and all, we can see a change in pressure as we go up because of these molecules being squished down to the bottom. Also, half the atmosphere is really below 18,000 feet. Think about it. Half the weight of the atmosphere is within 3.5 miles of the surface. And if you went up 32 kilometers, 99% of the mass is there. So air pressure drops really quickly in the vertical because of mass. Here's a surface map. We've seen these. And there's the isobars in millibars. You can see the low pressure. So the pressure is less here. There's less number of molecules and all there. More molecules here, higher. And here is how the pressure changed at one point with time. And you can see pressure was up here and it gradually dropped down. That's a low pressure coming, because what was one of the questions several of you answered. And the very first thing, when a low pressure or a cyclone is moving towards you, what happens to the pressure? It drops. Now, rising air temperature. We learned this past week that when you have air temperature increase, molecular motion increases. There's an increase in kinetic energy. All right, the atmosphere is not a closed container. So when you increase temperature, the molecules are going to tend to hit each other and spread apart. In other words, to be less molecules in a given area, the hotter the air is, so the density will be less. The air will weigh less. However, the colder it is, the molecules are going to be pulled tighter together, not pushed apart as much. Density will weigh more. The air will weigh more. So the colder the air is, the molecules are tighter together. It means if we go up in the vertical, pressure is going to decrease much quicker then, oh, I'm down in the tropics. Everything's very spread out here. It's very hot. Pressure we're going to drop much slower as we're going up in the vertical. And guess what? There's an interesting fact that water vapor weighs less than air. So the more water vapor in your air, those molecules weigh less than a normal air molecule. So since they weigh less, that means there's more, as there are more of them in there, that parcel of air will weigh less than the surrounding air where there's less water vapor. So if you have very hot air and very humid air, that will weigh significantly less than cold, dry air. That's why cold air masses tend to be the densest and usually produce high pressure. Warm, dry air masses will exert more pressure than a warm, humid air mass. So what can cause the pressure to change then? We talked about temperature doing it and moisture. One other thing, air converges. In other words, sometimes when you're outside, you can feel the air blowing very hard. Well, think about it. If you had something stationary, like a building there, the air is pushing into that building. The air is converging on that building. In other words, or you could have air coming from two different directions at you at the same time, converging air. If air is converging, it's pushing more molecules into a certain little area that is going to increase the air pressure. And because the atmosphere responds to this, if that convergence is at the top of the atmosphere is going to tend to push those molecules down to the ground. At the bottom of the atmosphere, they're going to tend to spread out. There'll be divergence at the bottom, and you wind up actually with higher pressure there. So these divergence and convergence of air can impact the pressure that you're going to learn about more. We just looked at isobars. Almost all isobars at the surface are generally done at 4 millibars. And they have 1,000 millibars and then 4 millibars on either side of it, all the way up and all the way down. We're going to look a little bit at the ideal gas law. So pressure and temperature, if you don't change density, are proportional to each other. The same holds for temperature if you're proportional to pressure and density. All three variables can change simultaneously, or two of them may be the same. It gives you a way, the temperature, to calculate pressures, temperatures, and density all. If I know 2 out of 3, I know the other one. And as part of that, then, we know air molecules spread out as they go up. If they go up and they spread out, and as you think about it with a bike tire, you let the air out of the tire, it's kind of cold at first, that air, because they're spreading out. When the air spreads out, it cools. When the air is pushed together, it warms. So when the air is descending in the atmosphere, it's going to get warmer. When the air is lifting up in the atmosphere, it's going to cool. And that is a thing you really need to know in this course, because you're going to be asked that question a lot to look at things. And the first law of thermodynamics says you gain heat when an air parcel either increases the particle's internal energy or it uses it to do work on the outside. Well, if an air parcel is rising in the atmosphere and expanding, it's doing work to push the other air parcels away, molecules away. So the temperature is lowering. If it's getting pushed in, the work's being done on it, so it is gaining energy. That is the reasoning for what I've just said. And here you can see that same exact process. So if I know this, and I know the standard atmosphere, I know the standard drop in pressure, I can calculate a lapse rate. And we're going to say this is dry adiabatic because we don't want to talk about water vapor at the moment. And I can tell you that temperature will drop 9.8 degrees Celsius for 1,000 meters, or roughly 5.5 degrees Fahrenheit per 1,000 feet. That is why when you go up the mountainside or down, when you're coming down it, temperatures are changing. And they're changing at that rate if you don't have any moisture around. Finally, moisture makes a difference. And we're going to go into why that is in the next group of chapters. So this is just a beginning here. I wanted to just show you one other thing here. This is a meteogram. Look at the bottom of it. It has temperature, it has time, the date and time. Here's February the 7th. And here was, we'll say, right around midnight on February the 6th, Friday. This is Pittsburgh Airport. I wanted to notice something. We're plotting temperature, dew point, and relative humidity. So right at this time, temperature was 26.6, dew point 24, humidity 92%. Probably snowing a little bit at that moment. However, not more than about 15 minutes later, the temperature is 17. Relative humidity is down to 67% and the dew point's 8. What happened? Cold front went through. So this is a classic example looking at a meteogram of seeing a cold front. Monster dew point drop, monster temperature drop, and the relative humidity, because the dew point drops so fast, is going down. So let's look at pressure. So if I looked at sea level pressure here, down pretty low here, going down, right here somewhere, begins to pop up again pretty close to where that cold front went through. Density began to increase, the moisture began to go down, and the pressure really took off, increased pretty quickly here. So you can see the influence of temperature and moisture on pressure. Now, one final thing I wanted to show you here is we talked about the pressure change in the vertical. This is 850 millibars. If I am over, say we're at 1,000 millibars in northern West Virginia, eastern Ohio here right now. Above that, 850 millibars is at about 1,492 meters. So maybe a mile up. In that first mile, you lost 150 millibars. We just looked at pressure that when the cold front went through, what did we see? About 20 millibars, maybe. This is so much more significant. The pressure drops so much faster in the vertical over a short distance. Something we're going to talk about later in this course. So this is just giving you an idea of how pressures and temperatures are related and densities and all. So it gives you an idea of where the high pressure might be, what it might mean. Temperature has probably a greater density because it'll probably be drier, probably be colder. So let me know if you have any questions about this.